Welcome to the video key for quiz 7. So we have a reaction that's at equilibrium. We're going to perturb it. That sounds like Le Chatelier's principal problem. And for that, we always want to write out the Q for the reaction of interest. So products over reactants. Remember that pure solids and liquids have an activity of 1. So we can just plug that in. So looking at this, what happens if we expand the reaction vessel? Well, we can see if we expand the reaction vessel, the concentration of ammonia and hydrogen chloride are going to go down. Well, if those go down, we can see that Q is going to go up. That means that K is going to be smaller than Q, at least initially. So when that happens, the reaction has to go backwards. Reaction goes backwards, we're going to increase the amount of our reactants, including ammonia. Oop, wrong one. We're going to make more ammonia. Okay, second question, what happens if we add ammonium chloride? Ammonium chloride is a solid, so no matter how much we have in there, the activity is 1, so Q is unchanged. If Q is unchanged, and we didn't change the temperature, so T is unchanged, we can see that nothing happens to the reaction. Which acid is stronger? Well, pKa is equal to negative log of Ka. And Ka is our equilibrium constant for an acid dissociating in water to form the anion and the hydrogen ion. So with that being the case, we can see that if we have a bigger Ka, we're going to have a greater tendency to be a stronger acid. We're going to give off more hydrogen ion. So let's do a little experiment. Let's take two different Kas, and we can see that these are both weak acids, but the stronger one is this one with the 10⁻⁴, right? It has a bigger Ka. So here's some Kas, and we can see if we use this formula of pKa is negative log of Ka, we get a pKa of 4 and of 6. So clearly the acid with the that's stronger is going to be the one with the lower number for the pKa. We wish to protect a plate made of tin from corrosion. How could we do that? So we've got a plate. Well, let's make it a plate of tin, and maybe it's buried, maybe it's part of an underground installation, and we're afraid it's going to corrode, so we put in some maybe magnesium. The magnesium corrodes. When it does that, it creates electrons that can run in this connection wire over to here. By putting electrons on the surface of the tin, we're going to make it be a cathode rather than an anode. So oxygen could go up there, grab some electrons, get reduced. And I'm not going to balance that, but you get the general idea. Now for this to work, we need to have a metal that is got a more negative reduction potential. Okay, so we need to look at a table of reduction potentials to see which metals are more negative than tin. Now, if we look at our tin reduction potential, we can see it's over here. So we want some number that's more negative than that. And if we look, what's below tin? We've got nickel, we've got chromium, zinc, aluminum, magnesium. So let's see if any of those are possible answers. And we can see indeed several of them are here. Chromium, aluminum, nickel, and magnesium are all more active. We say they're more active than tin. They have a greater tendency to get oxidized. Silver is quite electropositive. It has a great positive reduction potential, so not silver. Okay, we can predict as a general rule that salts with larger charges will be, and then the correction that was on here was less soluble. So we go to our table of potentials and we see tin here, and then we look and say what metals are more negative. And if we look down here, we see some that were on our list. Magnesium, aluminum, chromium, nickel. Those were all on our list, and they all have reduction potentials that are more negative than tin. So if we go to our problem here, we can see that we should circle several of these, right? So we've got, so all 4 of those would be good candidates for a sacrificial anode. Silver's not because it's so electropositive. All right, so we know in general that salts that have a more negative, that have a higher charge density, like aluminum phosphate, these are less likely to be soluble in water. Well, why? Well, it's not because of the lattice entropy, which is going from solid to gas phase, because basically we go from locked in a lattice to being a gas. We gain a lot of entropy regardless of our charge density. When we go from gas to aqueous, that's a different story, because obviously the ions lose entropy when they get plunged into water. They can't move around as fast, but also the water molecules get oriented around nearby ions. So these water molecules, which used to be able to spin around in any orientation freely, are now going to be pointing their dipoles towards the sodium, so that we lose microstates of water, and that effect is strongly dependent upon charge density. So we have a more negative hydration delta S if we increase our charge density. Okay, a process is spontaneous. What does that mean? That means delta S universe is greater than 0, and delta S universe is a function of delta S for the system plus delta S for the surroundings. So we know that sum is greater than 0, but we don't know, how to attribute that between the two pieces. So more information is needed if we wanted to say something about delta S for the system. Okay, for this next problem, we have an electrochemical cell based on some reaction, and we can see a lot about the reaction by looking at this graph, because we can see over here we've got reactants, and over here we've got products, and they're the same energy. So that means that delta G standard is equal to 0. Products minus reactants is 0. And because delta G standard is equal to negative RT log of K equilibrium, the only way to get delta G standard to be 0 is if K is equal to 1. So we can say that right away too. You could also see that the bottom of the curve, the bottom of the G energy curve, is right in the middle between products and reactants, so K is equal to 1. And that can help us answer our questions, because we know that delta G standard is equal to negative NF E standard. So since delta G standard is 0, we can say E standard is 0. That's over here. What about this other one? Well, we can say that there's a couple ways to solve this number 7. One is to say that delta G itself is equal to negative NFE. So both of these are not being standard, right? So what's the sign of delta G? Well, is this reaction going to be spontaneous forward or backward? If we look, our state of our system is given by this dot. We can see to go down in energy, we have to go backwards. So the forward reaction is not spontaneous. So we can see delta G is a positive number. And you may remember that the slope of this curve over here is negative, and over here the slope is positive. So we can see if this is positive slope over here, that means delta G is positive, delta G is negative over here. So depending on where you are in composition, you're either going to be spontaneous forward or backward. And where we are here, we're spontaneous backward. And so delta G has to be a positive number, and that tells us that E has to be a negative number. What about the size of K equilibrium? We already said that's equal to 1. What about the size of Q? Well, if we look at this, we said the reaction is not spontaneous in the forward direction. So if it's not spontaneous in the forward direction, we can say K equilibrium is going to be smaller than Q. And since K equilibrium is equal to 1, we know Q must be greater than 1. So we can say that over here. We can also sort of look at our diagram and say Q is given by our position on the graph here, and we can see that's on the right-hand side, we're greater than 1. So it's the same story. Which of these molecules are most soluble in decane? So we draw a decane. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can see it's a hydrocarbon, it's not polar, so all we have is London dispersion interaction. And so we want to match this to a molecule that also just has London dispersion interaction, and that would be this other hydrocarbon here. The other molecules have dipole-dipole as well as London dispersion, and this molecule would have dipole-dipole and H bonding with other molecules like itself. And so it's not going to be as good a solvent for, or it's not going to dissolve as well in decane as this center molecule. Okay, so we have a problem where we're going to try to generate oxygen, and obviously this reaction is one that's not going to go by itself. We have to supply some energy. So this is going to be something where we're using electricity as a reactant. So it's a stoichiometry problem, like an electroplating problem. Okay, so let's do a roadmap before we start. We sort of maybe one way to approach this is to start with what we know. So we know how much oxygen we want to make. So you've got oxygen, mass, and with like any stoichiometry problem, you want to get moles of oxygen. And then we need moles of the other reactant, or the reactant. Now the reactant in this case is electrons. And moles of electrons, we could convert that to charge. And so we can relate that to charge, and charge, we could get that if we had the time that we ran current through our apparatus and the current. Okay, so that gives us our roadmap. So to do the roadmap, we have to, well, let's just start writing some numbers down. So we have to be careful here because there could be some red herrings. Okay, so red herrings are things that they're there, but they're not real information. They're just going to distract us. Okay, now to do a problem where we're doing electrochemical stoichiometry, we care about current, but we don't care about voltage. Okay, and also we don't care about temperature. Now those things would be relevant if we were measuring the voltage, but not if we're trying to do it in one of these stoichiometry problems. And so in real life, the problems you do will be rich context. That is, there'll be lots of information that is relevant and then some information that's irrelevant. And so to be able to use your knowledge of a field, you have to be able to extract relevant details from irrelevant ones. So to make this a more realistic test of your knowledge, there will be red herrings in most problems. Otherwise, we're just going to fall into that illusion of mastery again. Okay, so let's go ahead and get started on this. So we're going to have 41 grams of oxygen. And we want to convert to moles. And notice that it's O2, so we want to write 32 grams of oxygen for every 1 mole, right? Because we're not doing oxygen atoms, we're doing oxygen molecules. And then we have, we want to go to moles of electrons. Okay, to do this part, there's a couple different ways we could do this. One is we could just use oxidation numbers. The other way is we could try to look up some half reaction to figure this out. So one method is to say, okay, I've got oxygen here, it's in a compound, and that means that it is -2, because it's not a peroxide, so it's just going to be -2 like it always is in compounds. And over here I have oxygen, it's in its elemental state, so it's going to be 0. So each oxygen atom had to lose 2 electrons. And oxygen tends not to lose electrons, right? That's why we have to put electrical energy in. Now there's 2. If we look at that, in every oxygen molecule, there's 2 oxygen atoms, which means overall we had a loss of 4 electrons total, right? So 2 electrons per atom, there's 2 atoms, so 4 electrons. So 1 mole of O2 is 4 electrons. We can also use our table of reduction potentials to see that as well. So I'm going to take you back over that table. You can see we've got 2 reactions with oxygen gas, where the oxygen is going to be reduced. So in this case, we were still going from oxygen 0 to oxygen -2, and so notice that's 4 electrons, and you can see the same up here that we went oxygen 0 to oxygen -2, and it's 4 electrons for every oxygen molecule. So you can use oxidation numbers, but you could also use this table as sort of a way to check yourself to make sure you're being right on that. So it's a transfer of 4 electrons. And so we've got, for every mole of oxygen. So we got 4, and I should say 4 moles of electrons. Okay, so we've got moles of electrons, and now we want to do charge. And so on these problems, the conversion factor between moles of electron and charge is Faraday's constant. So 1 mole of electrons is 96,485 coulombs. So now we've got charge. Okay, and now we have to go to time and current. Well, one of these we have, and one of these is the unknown. So our current is 230 milliamps. Now, whenever you write problems like this, you want to get rid of the prefix and just put it into scientific notation. And it's also useful to split composite units like amps into their pieces. So an amp is equal to a coulomb per second, right? It's how much charge is flowing past a particular spot in the wire per second. So that tells us where we want to put this, right? We want to put this on the bottom and say we've got millis 10⁻³rd, so I could just move the decimal place. So I've got 0.23 coulombs for every 1 second. So now I can cancel coulombs, and I've got seconds. And so now let's do one more thing before we go on and say if this makes sense for the time. This says the more oxygen that we want to generate, the longer it's going to take. Okay, that makes sense. This says that the higher the molar mass of oxygen, the less time it would take. That makes sense because this means the higher the molar mass, it means that for a given mass of stuff, it's fewer moles, and fewer moles would be easier to generate. This 4 is on top. Does that make sense? It does. It's increasing the time because even though we only want to make a certain number of moles of oxygen, we have to make 4 times as many, or we have to produce 4 times as many electrons to get it to work. So that should be on top. All right. There's a lot of coulombs for every mole of electrons. So the fact that that's on top and making our answer bigger makes sense. This 0.23, that makes sense as well, because if we turn up the current, if we were supplying more current, we expect that it would take fewer seconds. So that makes sense that it's on the bottom. So you should do that set of analysis as well. So don't just cancel the units, also go through and say, does it make sense that this is on the top? Does it make sense that this is on the bottom? Okay, so we plug all that in, and we're going to get the number of seconds. Okay, so you get 2.1 times 10 to the 6th seconds. All right, number 13, we drop a block of solid copper into a bucket of ice. The block has a certain mass, okay, and some of the ice melts. All right, we want to know how much melts, and the ice is already at 0 degrees C. Okay, so let's start with looking at the ice. So some of you drew a melting curve, which is a really good idea. So okay, gas, liquid, solid, so temperature and heat axes, and we can say the ice was already here, so we don't need to heat it up. All we're going to do is melt it. And we can see also it says some of the ice melts. Well, if not all the ice melts, the final temperature has to be here. So we're never going to go above 0 degrees C. So we're not going to heat up the water. All we're going to do is melt it. So we can see that there's 2 things here. We can say Q melt plus Q copper has to equal to 0. So the block is solid copper, and we're going to drop it into ice. So we can't melt the copper. All we can do is cool it down, right? So it's going to remain solid. So we can't use this equation because the Q's are not in the problem statement. They're not things we can't look up Q, right? That's not some constant. So we have to put this in terms of constants. And so we'll start by a series of steps converting these to either have these symbols, MC and TC, but also things we could look up. So the heat of melting is going to be the number of moles of ice that melts. And that's actually going to be part of our answer, right? That we're looking for how much ice melts times the heat of fusion. And then we've got the copper, and all we're doing is cooling the copper down. So that's going to be the mass of the copper, the heat capacity of the copper, and delta T for the copper. That's all equal to 0. So this hasn't gotten to how the mass of ice that melts, right? It's not moles of ice we want, it's mass, but we're getting closer. Okay, so we can see if we got the moles of ice, we could get a little closer to our answer. So we want to solve for moles of ice. Now we have to make sure that we reread our expression, our question here. It says only symbols, not units, good so far, but the symbols have to be either given in the problem or things we can look up. And if we look, we can look up the heat of fusion. That's definitely something that's on our equation sheet. The mass of copper was given. Heat capacity of copper we certainly could look up. What about delta TC? Well, delta TC, that's not something we could look up. What's given is the original temperature of the copper. So we're going to have to expand this term a little bit. What about the moles of ice? Well, moles of ice would be mass of ice divided by molar mass, and then we could look that up. So let's expand this a little bit. So we've got mass of ice divided by the molar mass of water. And we could use any symbol we want as long as I know what you mean, that's fine. We've got delta H of fusion. And then we've got mass of copper, heat capacity of copper. And we've got T final for the copper minus T initial for the copper. And the initial temperature of the copper, which is this TC that was given, is equal to 0. Okay, now we're almost there because mass of ice is what we're looking for. That's our unknown. And these other things, they're all things we could look up, right? We could look up the heat capacity of water, of copper. We've given the mass of the copper block. The temperature of the copper at the start was given. But what about this? This was not given. So we can't have that in our answer. But remember, we can see that since only some of the ice melted, that there was leftover ice. We must have ended up at 0. So now let's go ahead and expand this out a little bit more. So we've got the mass of ice, delta H of fusion, over the molar mass of water. And then we have plus this heat capacity for copper. And we have 0, and we have TC. Now at this point, when we have our definitions, we probably should have a definitions page somewhere in our solution where we say what our variables mean. We'll show that at the very end. Okay, so now, once we've defined it this way, we have a pretty simple expression because we can say we've got M for the ice, delta H of fusion, over the molar mass of water, and then we'll distribute this negative sign to get minus MC times the temperature of our copper. All that's equal to 0. So now we can move this negative sign over to the other side and solve for the mass of ice. So to do that, we're going to, like I said, we're going to move all this over here. So it's going to become positive, and then we'll solve for the mass of ice. So the mass of ice is going to be equal to M copper, C copper, the original temperature of the copper, and then we're dividing by the heat of fusion. And we're going to have to multiply by the molar mass of water. All right, so there's our final answer. We're going to stop and see if it makes sense. We'll do this a couple ways. One is to look and see that this says that the bigger the molar mass of water, the more mass of ice that's going to melt, right? Because we're going to melt a certain number of moles, so the more those moles weigh, the higher the mass of ice that we melt. The more copper that we throw in, the more ice we're going to melt. That makes sense. The higher the heat capacity of the copper, the more ice we melt. Makes sense. The higher the temperature of the copper, the more ice we melt. Makes sense. Heat diffusion is on the bottom. So it says the harder it is to melt ice, the more energy it takes to melt ice, the less we're going to melt. So that should be on the bottom. So that makes sense. We can check our units here. We've got our molar mass, which we could put in grams per mole. We've got our mass, which we could, if we wanted to, we could put our mass in grams. We have our heat capacity, which we could put into as joules per gram per degree C. We could put our temperatures in degrees C if we wanted. And the bottom we have our heat diffusion, which we could put in as joules per mole. So let's see, the moles cancel, the grams cancel, those grams cancel, the joules cancel, the degree C cancels, and we're left with grams. So the dimensionality works out. Whenever you do a problem like this, it's probably a good idea to have a key where you just define the symbols. So some of them are given in the problem, but I didn't take off for this, but it's just a good idea just for your own purposes when you're doing a problem. And it could help with partial credit to put in how you're defining things, like that this is the molar mass, let's see, actually that was already given, so we don't have to put that in. The heat capacity of copper is the specific heat of copper. And what else did we put in? Oh, the heat. And some of these are sort of self-explanatory. That this was the heat diffusion. Okay, so that's how we do a problem like that. Number 14. Suppose. Okay, so we run this reaction, and we want to find the voltage of the cell that we run from this reaction. Okay, so this one, we do want to calculate the voltage, and so this is going to be something where if we look at the concentrations, none of the concentrations are standard concentrations, so we're going to need the Nernst equation. So E is equal to E naught for the cell minus RT over NF log of Q. So then we need to find these pieces. We need to find the numerical value for Q. We need to know how many electrons are being transferred, and we need our standard cell potential. So we got to break this down into a bunch of pieces. Okay, and so first of all, let's figure out the potential for the cell, standard cell potential. So E standard for the cell is going to be E standard cathode minus E anode. Okay, so we have to figure out what's being oxidized and what's being reduced. So if we look at this, we can see our aluminum is going to be oxidized. This is our anode, because we're going from 0 to +3, and our oxygen is being reduced. So we're going from oxygen 0 to oxygen -2. So that's our cathode. If we look at the hydrogen ion, it's +1 as hydrogen ion, it's +1 as water, so nothing's happening to it. So that means we can look up the reactions. So let's do that. So we can go to our equation sheet and look for reactions with oxygen. And we can see there's an oxygen reaction here that involves oxygen and hydrogen ion being, and the oxygen gets reduced to water. So this is exactly the one we want. We can just copy that if we wanted, or we can just look for the number. So the cathode is 1.23. And the anode was aluminum being oxidized, and that was -1.66. So we've got 1.23 minus -1.66. So we've got 1.23 volts minus a -1.66 volts. And there was a tendency for students to want to multiply these by 3 or by 4. We don't do that. Cell potentials don't change when you multiply a reaction because they're joules per coulomb. So if you double a reaction, you double the joules, but you also double the coulombs. So don't multiply by a number, just use the numbers as is. So if we look at this, This is basically subtracting a negative, so it's going to be adding together. So we're going to get 2.89 volts is the standard cell potential. Okay, so we've got this piece. So now we have to figure out the other piece. Well, if we look at this, we can see that either by looking at the half cells on the previous page that I just showed you, or just looking at the aluminum, you can see the aluminum is losing 3 electrons, but there's 4 aluminums. So we can see that N is going to equal to 12. Okay, and the oxygen, each oxygen atom is going from 0 to -2, but there are 6 oxygen atoms, so that's going to be 12 electrons. So either way you can look at it, you can see it's 12 electrons being transferred. So we got that piece. So now we do need Q. So we have to write out an expression for Q first. Let's write that expression. So it's products over reactants. So we've got aluminum, and we're going to put that to the 4th. We've got we've got hydrogen ion, and that's going to be to the 12th. And then we've got oxygen, and we normally use the partial pressure of oxygen for gases. That's the default standard state. So partial pressure of O2, and that is going to be to the 3rd. Okay, that's not obvious that the default standard state is concentration. So if you converted it to concentration rather than partial pressure, I didn't take off for that. Okay, so we need these concentrations. 2 of them are given, but the hydrogen was given as pH. So we have to remember that pH is equal to the negative log of hydrogen ion. So negative pH is equal to the log of hydrogen ion. And so the inverse operation for base 10 log is 10 to the x. So 10 to the negative pH is equal to the concentration of hydrogen ion. These should be concentrations here. Okay, so if we plug that in, we can say hydrogen ion is going to be 10 to the negative, and the pH given in the problem was 4.5. So a lot of redox reactions have acid as a reactant or product, and so they're very highly pH dependent. Okay, so we have that number, so now we can write our Q. So Q, in terms of numbers, aluminum concentration was 0.01. And then we had the hydrogen concentration was 10 to the negative 4.5. And that is going to be to the 12th. And our partial pressure of oxygen was 0.2 atmospheres, and that is to the, that's cubed. All right, so we plug all that in. And we get 1.08 times 10 to the 48th as Q. And so now we can plug in all the pieces. So E is equal to E standard, which was 2.89 volts, minus 8.314 joules per mole per Kelvin, times the temperature. And the temperature was given as 298 Kelvin. And we divide by the number of electrons and Faraday's constant. Yep, that's coulombs per mole. And then the log of Q, so 1.08 10 to the 48, right? So since our hydrogen ion concentration is low and we multiply that, or the exponent to the 12th, we end up with a very small number on the bottom, which makes the overall Q quite big. All right, now remember when Q is big, that pushes the reaction backwards. And so if we make Q really big, we could actually decrease the voltage quite a bit. And in fact, we find that when we add all that in, let's go ahead and cancel units. Kelvins cancel kelvins, per mole cancels per mole, and so we have joules per coulomb, which is a volt, right? So we're subtracting a volt from a volt. We get 2.65 volts, So the actual potential is quite a bit less than the standard potential because we have basically a lot of, if we look at the ratio of products to reactants, we have these very low numbers over here, especially for the hydrogen ion. So the ratio of products to reactants is too high. That pushes the reaction backward. All right, that's the end for the video key for quiz 7. Thank you for watching.